Hi, my name is Daniel Beveridge. I'm Director in the Advanced Technologies Group within Office of CTO and VMware. And today we're going to talk about a new edge analytics solution that I've been working on with my colleagues Domino Valdano and Scott Chadley from NGD Systems. The presentation is divided into 4 parts: brief overview, a section on computational storage with Scott, a deep dive on Tanzu Greenplum with Domino, and lastly, a wrap up with myself talking about how the solution ties together. So the goals of this project, which has been funded within our XLab incubation program, is really to look at what's going to be happening in the area of edge analytics to drive toward the creation of a solution that incorporates higher density of data so that we can accommodate the vast amounts of data we see being generated by IoT, and especially video data. People talk about video as the new universal sensor. We're seeing a lot of pickup in the use of 4K and even now 8K video in a range of security, surveillance, and industrial use cases. Secondly is AI. With all that data being generated, we need a way to quickly make sense of it. So a lot of artificial intelligence and machine learning techniques are now moving to the edge. There's still a lot going on in the cloud, but edge is the area where people are looking increasingly to make sense of that vast amount of new class of data. So we'll be taking a look at how we can use some new methods and techniques to bring that AI all the way to the edge. And lastly is resiliency. With complex edge systems increasingly in the critical path, we need to make sure that they stay functional across outages, especially at far edge locations that may lack IT support. So we'll be talking about how a range of technologies contribute to resiliency in this solution. So what are the key solution elements? Number one is computational storage. Computational storage is the general movement of bringing compute to storage. Traditionally, storage was its own silo, and you would always move data to the CPU for processing. But in recent years, we've seen a new trend, which is to leave the data in place and increasingly move compute and services to where the data is being generated. Computational storage is a manifestation of that movement in hardware, and we'll be talking about the technology that NGD Systems has been developing to make that possible. Next, we'll move and talk about parallel database architecture and integrated analytics. So why is this important? Traditionally, again, databases have allowed you to store lots of data, but it had to get moved across a bus into a main CPU for processing. With parallel databases and integrated analytics, you have the opportunity to have a database infrastructure that can make use of multiple nodes in parallel and actually perform the analytics right in the database instead of moving it to a remote CPU. This turns out to be a particularly great fit with computational storage. And we'll see why more. We'll see more about why that is when Domino presents. Last but not least, we have the contribution of vSphere itself and vSphere Bitfusion technology. vSphere provides the underpinning for the reliability and resiliency element I mentioned. vSAN technologies like fault tolerance and the GPU acceleration provided by Bitfusion will turn out to be an interesting contribution and key to meeting the resiliency goals of this solution. So what are the key business outcomes? From a business standpoint, what we're really trying to achieve is a high-density edge solution that can be deployed with less servers, lower cost, less power. We also want to move AI effectively to the edge, including both inference and training, so that we can cut out dependency on always having to ship that data back to the cloud. And that's particularly important at the far edge where you have narrow bandwidth and insufficient bandwidth often to move large data sets to the cloud. Lastly, we want a reliable solution the business can trust so they can actually put edge analytics in the critical path with the business and can rely on it even when IT is not present. So with that, I will segue to Scott Chadley, who will talk more about computational storage. Scott?
Thank you, Daniel, for the great introduction. As you can see, I'm standing virtually outside the Irvine, California headquarters of NGD Systems, where we build computational storage drives. Our unique technology takes the standard NVMe SSD and adds what we call in situ processing inside. So what I wanted to do today is spend a few minutes before we get into the further information from Daniel and Domino is talk to you about what is computational storage and why it matters. So as you can see here on the left-hand side, as we went about developing this technology, we did a big market survey and we said, what are the pain points? What is it that's causing so much trouble for our customers to be able to deliver their products? And those pain points consisted of physical space, the amount of available power, the scaling mismatch. Just look at the idea that there's no such thing as one-to-one between compute, memory, and storage today, let alone the addition of things like GPUs. And that's the whole purpose we have VMware and virtualization, is to help bring some synergies to all that, and we help leverage that even further. And then, of course, the bottleneck shuffle. If it's not the storage device, it's the memory. If it's not the memory, it's the CPU. If it's not the CPU, it's the PCIe Gen 3 versus Gen 4 versus whatever bus that may exist. It's the fabric. There's latency somewhere in the Ethernet of the world. So what we're trying to do here is look at that traditional structure of a CPU plus DRAM plus storage that we all know and love. And we've taken these different pieces and we've looked at how to scale them. We can scale CPUs, we can scale memory, we can scale storage. We can do this with JBODs, JBOFs, lots of really unique, innovative ways to do things with memory. And even the CPUs themselves have continued to gain traction and direction. But at the end of the day, if you take a simple server, one storage device, or one CPU, a whole bunch of DRAM, and a lot of storage devices, these technologies don't have a perfect match to one another today, and we all know that, and we find ways around that. We've found things like composing these elements. So we compose CPUs, we compose memory, we compose storage. There's some great solutions that do exist with VMware and our partners in this project as well. However, there's a new way to look at this and stop saying that storage is just something that sits there and holds my information. I've got this great batch of data. I really need to do something with it. And how do I get to that next logical step? So what we said is we're going to add some scalability to the storage devices. Now, this is not something that's brand new in the marketplace. It's been around for a few years, but it's never been optimized, energized, and focused direction that exists now from something like the NGD solution. So what we've done is we've added a capability from a distributed processing. We've made it very fast because we're now bringing the ability to get results from the data at the data source, no longer at somewhere down the pipe. The road is no longer as long. The lanes don't have to be wider to make more traffic. We can simplify that solution. We also draw much less power because we're not utilizing the CPU in ways that it's not meant to be done. Think about very simple tasks like searching for something. Do you really want to run around your house all the time looking for something, or do you occasionally yell up the stairs and say, hey, where is it? That's the type of technology solution that NGD is bringing to us today. And of course, footprint is a big thing. As we look at the edge, we're talking about bringing massive amounts of data through autonomous anything. We've got all kinds of edge clusters, mechs, these really neat architectures, all utilizing VMware virtualization, but still have a footprint problem because of that traditional hierarchy. So we're scaling with computational storage products in a very seamless fashion. And so the simple example I show here is we take that traditional CPU, DRAM plus storage, and we're adding additional CPU resources into our storage devices. So you've heard of smart storage. There's lots of platforms out there that deliver smart or intelligent storage, but those are around data management. They're around how to make sure your data stays intact, how to make sure your data doesn't go away if you lose power, how to keep it clean, this concept of wear leveling and garbage collection that exists in an SSD. Our level of intelligence is a bit different. We're bringing CPU processing power, not just media management, into each individual storage device. So that you add a storage product to store more data, it can also compute on that data. And we've given it the nickname server in a server architecture. And this additional CPU resource added to the storage device, especially in today's marketplace where we're building larger and larger drives, the media is the driver of that cost. So these CPUs may seem like they might be expensive if you're thinking Intel, AMD. We took a very power efficient ARM core processor and stuck it in our device, and it literally disappears in the cost of the overall product because of the solution at the capacity points we're talking about. The media, the cost of the raw media is actually overweighing that. And as those come down, our processor costs will come down. And so there's scalability and even long-term viability of these products. So you may be wondering how we build these products and what are they? So we have designed from ground up a SSD controller, and that controller has your traditional everything about media management. We have firmware, we have everything to make this an enterprise solid state resilient drive. And the team here at NGD actually worked originally to build the first enterprise SSDs in the market back in 2007 to 2009. So we know what we're doing when it comes to an SSD. So we said, start simple, make sure you plug this device in, you can have fun with it, you can use it as a storage device, read and write to it all day long. And we put it in your traditional form factors. So when we talk edge platforms, the M.2 is a very popular product today because it fits into a very small form factor. Things like the Nook or drones or even some kind of edge-based platform sitting in a closet somewhere. The EDSFF, the nice little blue drive center of that picture that you're looking at now, is the new edge deployment form factor, which allows higher capacities, better power consumption, and even higher performance. And then, of course, we all know and love the traditional 2.5-inch SSD. So we're going to build those, and we're going to put them at a capacity point that no one else in the market has available today. Just think about the simple fact that a deck of cards can hold 32 terabytes of storage, and you're on the right track for what we can do with our solutions today. And then the real value of computational storage is the in-situ processing stack there on the right-hand side. What we have done is we've added a Linux OS. We've actually developed, deployed, and have in place the ability to SSH into a drive, load code, run code, execute data analytics, search, machine learning, AI, all inside a single storage device. And those ARM processors are powerful enough, power efficient enough, and capable to take localized data, manage it, transform your raw information, and deliver value back to the host with no additional work being done except for being able to give that processing in a distributed fashion. If I've got 2 drives in a system, great. I've got 4, even better. If we're going to do a full server, like the example that we're going to talk to in a bit, 24 drives means you get a significant amount of distributed, parallel, seamless processing. So one of the things we wanted to talk about, of course, is use cases. We need to explain to you how you're going to use it, because this is something a little bit different. Takes a little bit of thinking around how you can implement it and what we can do with it. And so what we're going to do is talk to a lot of different ways that we've already explored it with some of our customer base. So this is what I call an ASCAR chart. You can see here we have things like smart automation, edge and IoT. You can notice there's something even in there as far out as the edge, known as our low Earth orbit satellite engagements. And of course, you have your traditional data center content delivery, and of course, last but not least, the autonomous world. So think about a data recorder in the trunk of a car that's able to do machine learning on the fly while it's driving down the street, because it has the processing power capable to do that that isn't sucking the batteries dry in the way of high performance GPU platforms and the like. So being able to take this, compute on localized data in a virtualized environment at the edge is key to the success of these types of solutions. And you can see we've done things like TensorFlow libraries. We're going to explore the Greenplum database with VMware Tanzu. We've got the capability to run things like MongoDB and Hadoop, all these different workloads, because, again, it's a server and a server. I've presented to you a Linux OS. I can do it at a GUI level. I can do it at a command line level. You tell me how you want to use it, and our drive is capable of offering those types of solutions based on that Linux platform. And if you don't like Linux, let us know. We can put a different OS. Again, it's an application CPU, fully capable of being fault tolerant, resilient, and providing enterprise level solutions through this particular controller that we've been able to design and develop and manufacture all here in the US. So when we think about that, here's a couple of brief examples that have already been deployed as we get back into Daniel and Domino in a minute. Things like MongoDB. You can see that we have the capability to accelerate performance results with no additional CPU, no GPU. Just by adding storage devices, you get faster results. Historically speaking, the CPU becomes the bottleneck because you have one processor talking to a whole bunch of devices. I've got 24 independent SSD controllers, all with a processor that are generating results and feeding those back for the main CPU to do the work. On the right-hand side, you see that I have some machine learning going on. Machine learning acceleration is another key one. There's multitudes of different types of machine learning algorithms out there. This is an example of 2. And you can see from just looking at the simple colors from blue to orange, adding more devices increases the capability of the community. So we're going to continue to work at this. We're going to continue to develop these solutions and be able to provide these types of products. And I wanted to give one live example. So this is actually going to walk through and show you how we're doing model training. If you look at the screen, you'll see in the top center of the page, this orange box is showing the CPUs that are on my device. So this is a single device doing training of a single object being watched by a camera. This blue box will show you the number of model updates that are occurring in this short period of time as this video clip runs forward. So as you can see, we're going to pick up this device and we're going to classify it, and we're going to pick it up and we're going to actually move it around. And as we move it around, you see the CPUs in the orange box are actually doing all of that processing, and the models are being updated real time in the blue box. So this is the concept of being able to take one or more devices, put the training model down into the device, and execute the commands without having to involve the host processor in any way, shape, or form for the low-level work. So as I get ready to turn this back over, I wanted to leave you with a comment from our friends at 451. Computational storage is an emerging technology, but will become commonplace in one form or another. I believe that as we go through the rest of this presentation, you'll see that there really is an opportunity for computational storage to deliver that value you're looking for, but in familiar form factors, familiar products, and the ability to drive the future forward with very limited and very successful transition in your architecture that does not require a complete and wholesale replacement of the technology. So once again, thank you for your time, and I'm going to go ahead and hand it back over to Daniel and Domino, and they're going to walk you through the rest of the presentation. Have a wonderful VMworld 2020.
Hi, I'm Domino Valdano. I am a staff software engineer at VMware, recently coming along with the Pivotal acquisition. Under Pivotal, now mostly called Mapu, I work on the Greenplum database. The Greenplum organization used to be under Pivotal, now we're under VMware, and we're excited about integrating with the rest of VMware's products. And so I'd like to give you a bit of background on Greenplum, as well as an extension to it called MadLib, which is what I work on specifically in the advanced analytics team. So when I think of Greenplum, I think of four main strengths. First of all, it's got all the traditional features of a traditional data warehouse, relational database, it's ACID compliant. Your data is not going to get corrupt or suddenly become inconsistent. There's a lot of robustness to it. It's also open source, which is really cool. And in fact, recently we were ranked the #1 open source the open source data warehouse in the world by Gartner. But the really cool thing is we're not just a traditional database that runs on one machine. Greenplum is a massively parallel solution that can run distributed on many machines at once. So it's designed to handle big data in the same way that a NoSQL database would, but with the familiar SQL interface that so many business intelligence analysts, data analysts already know how to use. They don't have to learn anything new. Here are some of the features that it has. It's got, you can do federated queries on it, integrating with AWS, G-Cloud, most recently vSphere. You can mix OLTP processing with transactional processing, analyze and transact at the same time. You can do time series data, graphs, geospatial, AI, machine learning. So this is basically the architecture that Greenplum has. It is based on the Postgres database. It forked off of the Postgres repository a long time ago. It has a lot of enhancements. So it's basically a lot of parallel running Postgres servers, and then a main host that is also a Postgres server which receives the SQL commands, forwards it on to all the segments, and then they process it. But the queries are also optimized by a special optimization accelerator, which figures out how to make it run very efficiently on all those segments. You can put multiple segments on each of these segment hosts, or you can just put one per host. And then typically you'd also have some mirrors. So in addition to those Postgres processes that are called primaries that are ready to respond to queries immediately, if any of those go down, then the mirrors are standing by ready to take over. And there's even a mirror for the main host called the standby that can take over if the main host goes down. So everything is redundant. And if any one thing fails, then you're not going to lose any data. So the software stack of MATLAB is basically SQL on the top and C and C++ on the bottom, and then Python in the middle. The terms UDF and UDA in this diagram refer to extensions of the Postgres language called user-defined functions or user-defined aggregates. It's a way of adding a new SQL function, but written in Python. You can also have UDFs or UDAs in other languages like C or R or SQL itself. It's one of the great things about Postgres, and Greenplum also takes advantage of that, and MATLAB uses it to implement its functions. So here's like a typical UDF of MATLAB, a very simple linear regression. So with any kind of supervised learning, you usually have a train function, and then you also have a predict function. The train function takes a lot of examples that are in the database already and labeled with labels that are correct in the case of categorization, or in the case of linear regression, we're talking about houses in this case. So the price would be what you're predicting. So those are essentially the labels. And then the train function spits out a model, saves that as a table, and then you run the predict function on the model, and then it'll spit out a price. So here's what the result would look like, the table that comes back as a result of that predict function. These are the features, the property tax, the bedroom size, bathroom size, lot size, etc. You can add as many features as you want, and it just looks at all of those, and based on all of the examples you fed it, it predicts what the new price is. So in this case, it's fairly easy because it's assuming all of those are linear, but we have much more complicated functions that can do all kinds of nonlinear inference and also unstructured, unsupervised learning, where you're doing more like data mining, analyzing clusters and looking for patterns in data, things like that. So another thing that I mentioned that MATLAB does, of course, is graph theory. Here's an example of a practical application for that is ride sharing. So you've heard of like, obviously, most of you have used like Lyft or Uber or some of these others, and but you may not realize how complicated the graph theory problems get in those situations. So let's say Alice is at her house and she needs to get from point A to point D, this schoolhouse, and the driver is picking her up, but there are also a few other passengers, or someone at location B, someone at location C and E, and they all want to get picked up and also go to places. Even if they're all going to D, it's still the question of like, which is the shortest path? So what is the, like, which way should the driver take that is not far out of their way? And then, of course, you don't usually have one driver that's trying to solve this problem. It's not the driver, it's the edge device that would be on board. You don't just have one edge device in one driver's vehicle that's trying to solve this problem. You have thousands of them all over the city. And so that's where the parallelism can come in handy. And maybe there's thousands of passengers and you need to solve a really big graph theory problem, in which case it can also break it up and run it in parallel. But the point of this graph is to show that even if it's just a whole lot of easy graph theory problems, which aren't too difficult, if you have enough of them, if you've got thousands or millions of them, you're going to need a lot of parallelism and a big database to work on them. So image classification is the final example I want to give you, and I'll give you a brief demo of both that and the graph theory next. But MATLAB uses convolutional neural networks to recognize and categorize images. So it uses Keras and TensorFlow under the hood. On each machine, it's basically running a Keras model in TensorFlow and using that to either train or predict with these convolutional neural networks. And MATLAB is coordinating all of this and shuffling the data around and basically mediating between the Greenplum database and Keras and TensorFlow, which are running, in this case, on these ARM processors. So how do you actually load an image into a database? A database, of course, is tables of columns of numbers and text, usually. So we break the pixels, individual pixels of the photos, the images up into multi-dimensional arrays. So these are like 256 by 256 by 3 color images, and therefore you got a 256 by 256 by 3 arrays. And then it also batches them up for the training so that you can efficiently go over like large batches of them. And then for the prediction, you get something like this as an output where it's labeling, this is a soccer field, this is a sky, etc. And finally, before we get to the demo, I want to show you Jupyter can be a really nice front-end interface for MATLAB. This is something that most data scientists now use on a daily basis. There's a big shift towards using Jupyter and Python for data analysis, usually with embedded SQL that communicates with the database anyway. So this is especially important for MATLAB because you would define the models here in Python, but then somehow you gotta get them into the database. So Keras will spit out a JSON representation of a model, and then you can, if you just have a SQL command line, for instance, you could cut and paste that in, but you can also just send it directly in Python code. It's just doing cur.execute and sending the model over to the database in one nice command, and it is sent in JSON. All right, so let's get to that demo now. So let's start with vCenter. So I'm going to show you here is how you interact with vSphere. So we have two edge devices. They're both Dell PowerEdge servers. This one is the .10 IP address, and then we've also got a .13. Both of them have tons of memory, tons of disk space. You can also look at them through the point of view of the iDRAC console, or you can log directly into the ESXi server. Both of them running ESXi, and on the first one we also have vCenter itself running as a virtual machine. The main virtual machines that we have configured on them are Ubuntu. Now you could run any operating system you want, of course, on these edge devices, but we've got one virtual machine with Ubuntu 18.04 and the second one with 20.04. The first one we've configured to host all the primary segments of Greenplum, while the second one is hosting all the mirrors in case anything goes down, so it can take over. So if we just were to launch a web client here, you could see the actual operating system running. You can see that it has a lot of storage here, all of these 2.0 devices. Those are the actual computational storage devices from NGD. So now what I want to do is just log in directly to one of these edge servers. So I'm on the edge server. Notice that this is we're still seeing an x86 architecture here. So we're not in the ARMs yet, but I just wanted to show you what it looks like from the point of view of the host server. Is we have we can see all of these storage devices. We partition them each into 3 partitions. They've got a total of almost 12 terabytes per disk. The first 2 of them just have typical Linux read-write file systems, whereas this one, the second partition on each, we actually have configured using OCFS2 file system, and the thing that's unique about that is it allows very concurrent reads and writes to happen to the same file system from totally different host machines. And that's good for us because it means we can mount the same drive and use it both from the host on the x86 side and from the computational storage device, which is running on an ARM. We also have a tunnel dev set up, which is a driver from NGD that forwards all TCP/IP traffic to the actual ARM processor. So it acts as a tunnel going between the two. And so you see all these interfaces here. Each one corresponds to a different storage device. And if I SSH, say, node 1, corresponding to tap 0 here, here we are on the actual ARM. So this one, and this also doesn't even have to have running the same operating system as the host. Right now it's running Debian, so pretty similar, but you see right here, now we have AArch64, which means 64-bit ARM processor. So that's pretty cool. Now we're running with ARM, and we've got a totally different separate CPUs and memory, and then we've got some separate storage and some shared storage. You can see the shared storage is here. If I were to write to a file here, then I can read from it on the other side and vice versa. So you can see that, so this one, node 1, is actually acting as the master node. GPDB has this utility called gpstate, which shows you the state of everything. So you can see that here all the primary segments, there's 6 primary segments, there's 6 mirrors. You can scale this as much as you want. We just set this up as a demonstration. It'll tell you if there's any failovers here and whether they're in recovery mode, what's happening. Everything happens seamlessly while you're operating, and it can come up. So if I just open like a typical Postgres client here, I can access it on the master node locally from the ARM. I could also even access it here. I'm on my Mac, and I could access it from here even. I just have to pass like some more credentials and to tell it to connect to the right host, and you have to make sure, of course, that the firewall rules are such that you can actually get into that host. And you should probably set a password, which I didn't. But so I'm looking at it from locally here from one end and here on there, and we could also access it if we want from the edge device. So you could have whatever software you want running on these ARMs separately from the main host, and they're pre-processing all the data before it even gets there. So if you're doing database queries from the main host, you could have images that are already filtered based on location tagging or different image recognition, throw away the ones that don't look like what you're looking for, and then pass the rest onto the main host. Okay, so I showed you how to connect via the command line and remotely from remotely or over SSH from a SQL client, and now I'm going to show you how to connect from a browser with Jupyter. So this is again something that a lot of data scientists use. In this case, I'm actually running things on 3 different machines. on my machine, I'm only running the browser and it's displaying this web page, but it's hosted off of the Edge device, specifically the Ubuntu virtual machine is running the Jupyter kernel. And that's what runs all of this Python code. Every time I hit enter here, I'm running some Python code. And the command I just ran connects to the database on node 1, which is the main host of the Greenplum database. So I've connected now to the Greenplum database, and from the main Edge device, the x86 CPUs are now connected, and then they can make queries. I've made 2 queries here for the version of Greenplum and the version of MadLib. We get them back, so that means we're definitely connected. And now we can just run a few sample problems. So I told you about that rideshare problem. Very simple graph theory problem, just 5 vertices, 9 edges. It takes an input in the form of these 2 tables, all the vertices and all the edges as an adjacency list. These weights would represent the distances between the nodes in the graph. And basically, if you're a driver and you're at node 0, which is our starting node, you want to know the shortest distance to all of these other nodes. And in particular, we're interested in node 3 because that's where the current passenger wants to get to. So the ones with higher weights, like 4, mean that there'd be more traffic there, or it's just a longer road, or it's uphill or something. It takes longer. And then a 1 would mean it's really quick. Some of these are 2-way streets, some of these are 1-way streets. That's why it's a directed graph. And you can always run usage on any of the MATLAB commands. So in this case, I'm running graph underscore SSSP, which stands for single source shortest path. So it's designed to solve the problem that we're solving. That'll give you all the instructions for how to run the command. And by the way, if you want more further details with examples and everything, you can always look at the online documentation also. So now I've just actually run this graph underscore SSSP. I intended to run after I got back from the other page, but basically it did return in less than a second, and I passed the input tables that I mentioned plus the starting vertex of 0, and then this is just telling it where to write the output. So it's going to write the output to this rideshare shortest path table. And if we look at that table, it's got this table contains all the information about the distances from that node to every node. It's a little bit hard to interpret though, so there's a helper function that you can run after that, which can just take this table and extract out of it the path to a specific node. And that's usually much faster. In this case, it took a half a second, but because if it was a much harder problem, then this would be way faster than the other one. So it's telling us that the path is from 0 to 2 to 1 to 3. And that's a total of 6 going to node 3. And so now let's do the same thing but in parallel. So I've created another table with 150 drivers, and they've all got the same problem to solve. I mean, in reality it'd be different problems, but to make it simple, I just made it the same. So the edge, so they've all got the same vertices, and they've all got the same edges, but then we can pass this with what's called a grouping column, this last argument here I added, which tells it to group by the driver. So it's going to solve each of the problems separately for each driver. And now it took a little bit over a second. So it took a little bit longer, but not really that much more, because it's doing a lot in parallel. We've got these 6 different segments all working together. And also because it's like a fairly simple problem, so there's more overhead in the first one. And then when you run this get path with it from the output of a grouping column call request, it gives you a separate path for every driver as an array. And one more graph thing, let's just say it was a much bigger graph. So I have this graph that has 10,000 edges and 2,000 vertices. And just to show you what that looks like, I'm going to render it like we did the other graph, except that this graph takes a long time to draw. So it actually takes longer to draw than for us to solve this problem for this huge graph. Like, because actually a lot of the drawing is on the client side, and I've only got one computer here, so it took a while to draw all of that, but then we can still solve the problem very fast. So I just ran it. It actually returned in less than a second, because it parallelizes the whole thing, and it tells me that, oh sorry, this was the second part of it, took less than a second, and then oh, the first part of it took 2 seconds. So it's a little bit longer, but it's not it's a much harder problem, really, trying to find a path all the way from here to here. And so it's pretty impressive, I think, especially considering we're doing this all on ARM processors. We're not using the main CPUs on the host at all for this computation. And there we go. There's our path from there. And if I wanted to just extract all of the paths from that answer that it gave, this is just coming from this output table that it resulted from. It's got the path from 0 to every single node in this graph, and it just goes on and on. So there you have it.
Hi, this is Daniel. I'm back to talk about how these various solution components we've been learning about all tied together to create a breakthrough in edge analytics. We've learned about computational storage from Scott and about Tanzu Greenplum from Domino. I want to talk now about the contributions of Bitfusion, vSphere, in terms of meeting the overall solution goals. So let's talk about how we have integrated the NGD Systems Devices to vSphere. vSphere has a feature called VM Direct Path I/O, commonly known as PCI pass-through, that allows us to map PCI devices directly into a VM. So in the diagram you see here, we have a virtual machine running Ubuntu. And on that VM, we've been able to link, in this diagram we show 4, but we can do up to 15 of these NVMe devices and mount them as though they were local storage devices to the VM. The Ubuntu sees them as local partitions, and we're able to use them just as we would a regular NVMe storage device. However, we also have a special TCP/IP encapsulation driver running on the VM. This is software created by NGD Systems that actually wraps TCP/IP in the NVMe protocol so that it can be sent along the PCI bus and communicated to the ARM chip that's embedded on the storage device. And it allows us to establish a true network link between the VM and the various NVMe devices we've got mapped into the VM. The net effect is that they appear as separate computing systems on your network, and you can ping them, talk to them just as though they were literally separate virtual machines or separate physical machines on your network. So the TCP encapsulation driver allows us to bridge the gap between these devices as storage devices and their role as separate operating systems. The third thing we did to integrate the NVMe devices with vSphere was to have a separate partition strategy. We had 2 partitions on each NVMe device. One was XFS. This is the local, highly secure journal file system which Greenplum installed on. And then separately from that, we had an OCFS partition, which is the Oracle clustered file system That partition is able to share files in real time with the VM into which the device is mapped. So the VM will see, let's say, 4 OCFS file systems, and it can access them all simultaneously as though they were local partitions. The XFS partition is not shared. It's used exclusively by the local Greenplum installation that's on the NVMe device. Now, the XFS performs a little better. In the test we did, it was closer to a gigabyte per second overall throughput, whereas OCFS achieved about half of that because of the file system overhead that it had. But the way we use the OCFS is to stage data that we may want to use for training. And the reason for that is that these NVMe devices have a memory limitation of about 6 gigabytes of RAM, for instance, which isn't really enough for training. It is enough for inference, however. But when you're going to train, you want to first do some filtering on Greenplum and then stage out data that you want to perform your training algorithms on. And you can stage that on the OCFS partitions. It can then be picked up by an instance of Greenplum running up on the Ubuntu VM that we call the jump box. And that can then be assigned a large amount of RAM and leverage a highly powerful GPU effectively. Our Bitfusion technology needs the assignment of about 1.5 times the GPU memory as RAM on the VM. So for example, if we're using a GPU with 32 gigabytes, we would need to assign, let's say, 48 gigabytes of RAM to that VM to perform the AI training and fully leverage the Bitfusion technology. Since that's not possible with the NVMe devices, it makes sense to do your training upstream on the x86 side of the host. And that's where the OCFS shared partition strategy comes in very handy, allowing us to stage the training data effectively and access it in real time without moving it around in advance on the training VM. The next element of the solution I want to talk about is the Bitfusion integration. We used VM Direct Path IO again here to map a powerful GPU into a VM that was running the Bitfusion OVA. Now, Bitfusion OVA is the machine essentially talks to the GPU and does the sharing of that GPU to its clients, which are mounted at various places across the network. That, as I said earlier, you need to assign quite a bit of memory to that Bitfusion OVA. 1.5 times the memory of the GPU is the best practice. So how do we GPU enable the computational storage? Well, what's interesting is that we were able to compile the Bitfusion CUDA client onto the ARM64 platform and run it directly in the Debian instance running on these devices. So the Greenplum installation itself actually believes that there's a local GPU running on the computational storage chip. In fact, the CUDA commands are redirected and sent out over the network to the Bitfusion OVA and are essentially executed on that local GPU. But in this case, the network is all inside the same host. As I said, the network is actually itself running across the same PCI bus using the TCP/IP encapsulation driver to move the traffic from the embedded NVMe devices to the Jumpbox VM and then on to the Bitfusion OVA. So what this allows us to keep inference on the NVMe devices for speed, but allows us to do the training on that jump box or a nearby box so that we can use an appropriate amount of memory and get more horsepower for the training itself. So this solution really relies on the redirection that Bitfusion provides to enable the inference side of AI. And on the training side, Bitfusion is again leveraged to train on the x86 VM upstream. So we're using it for both ARM clients and x86 clients simultaneously, all within a single host. So this is a unique solution because it's the first time that GPU enablement of computational storage has been achieved to the best of our knowledge. Bitfusion provides unique technology that allows us to project GPU resources into devices that are themselves would never be able to fit a GPU, things like a Raspberry Pi, or in this case, an onboard ARM processor on a storage device such as NGD Systems. This is really a unique approach and allows us to share a few GPUs at the far edge, but actually service a number of devices with intelligent resource sharing. Last but not least, we have the solution resiliency component that I spoke about earlier. Solution resiliency is really critical at the far edge because there typically isn't the IT resources to quickly step in and repair solutions. So that means you either have to assign solutions to non-critical path activities, or you may incur outages that create quite a lot of risk, cost, and concern for the business. So our goal with this edge solution was to also allow it to be pretty resilient. And we achieved that using a number of different technologies. One of those technologies was vSAN. So vSAN allows us to create shared storage between two nodes plus what we call a witness node. We used a 10 gig cross connect between ESX01 and ESX02 shown in this diagram to transit the vSAN traffic. And that allows us to have an application that actually queries the Greenplum database running entirely on storage, but that application can be resilient against a server fault. The reason for that is because the storage that it's using for the application itself, not its data set, the storage that the application is using is running on vSAN, and that will survive a host failure. The second element is fault tolerance. We also used a 10 gig cross connect to achieve fault tolerance for a VM that was running our AI application. In this case, it was pretty simple. We were testing with Jupyter Notebook and some other scripting applications, but we were able to show that they were resilient across a host failure. The third element is the Greenplum data itself. Greenplum has a built-in ability to mirror data between its primary nodes and its mirror nodes, completely bypassing the x86 host itself. So the mirroring occurs over the network between the primary and mirror nodes. So what we had was an equal number of nodes on the primary in node 1 and node 2. For example, if we have 15 nodes on node 1, we will have them being mirrored in real time to node 2 through the network. Now that network does go through that jump box on node 1, the jump box VM, but it's being mirrored in real time. So if node 1 goes down, there will already be a complete copy of the data resident on node 2 NVMe devices. They'll be able to pick up and recover from the failure of the Greenplum's primary nodes. So the other element that's important here is the Bitfusion server framework itself. It has its own quorum concept where it needs 3 nodes, and with 3 nodes, it's able to recover from the failure of any one of its 3 members. So if the node 1 goes down, the Bitfusion server will go down along with its GPU resources. But because of the way Bitfusion itself can recover, node 2 would step in immediately and continue servicing the GPU requests of the clients now running on node 2. So these combination of technologies, vSAN, fault tolerance, the Greenplum, Tanzu Greenplum data mirroring, and lastly, the Bitfusion quorum resiliency itself, they all function together to make this solution able to recover from a complete failure of one of the 2 nodes. We think this is pretty impressive. You get the speed and offload of the NVMe devices. You get the GPU acceleration of Bitfusion, but you get the advantages of shared storage for the actual recovery of node failure, something that vSAN is providing and is really the foundation of this far edge solution. So if you look at this solution in its totality, bringing together a number of advanced elements that each have their own advantages, but function together to give a high level of solution resiliency. So the key solution innovations that we think make this solution pretty special are, number one, the parallel use of computational storage, which frees up the main CPU, essentially giving a single host another up to 15 small CPUs to perform integrated data analytics. This allows you to use a less powerful server because a lot of the database pieces and the analytics is being offloaded directly to storage, leaving the main CPU free to run your AI application and to be used for the Bitfusion enablement and other maintenance functions. Essentially, though, bringing the cost of the server down, using less space, while giving you a lot more compute capability. The second element is GPU enablement of computational storage. This is where Bitfusion really shows its strength. Bitfusion allows a tiny device in an M2 NVMe form factor to effectively believe it has GPU capability and to perform GPU enhanced machine learning inference. The third piece is the advanced data center grade features that vSphere is bringing to the mix. This allows us to create a far edge analytics solution that has the uptime or can meet the uptime requirements that the business may require for critical path analytics solutions. And this includes, as I mentioned, the vSAN, the fault tolerance, and the high availability in general that we offer the solution. That also includes the Bitfusion piece I mentioned as well. So these are the three elements that we think are pretty unique in the solution and break new ground. And we're delighted to have been able to present this to you. We hope you get in touch with us to learn more about this and enjoy the rest of your VMworld. Thank you.